Have you ever stopped to think about what's really making your Android phone, or even the world's biggest supercomputers, run so smoothly? Well, today we're going to pull back the curtain on one of the most fundamental, yet pretty much invisible pieces of engineering that makes it all possible. We're talking about the unsung hero of the Linux kernel. So let's just start with this massive question right here. At any given moment, a Linux system is a whirlwind of activity. It's juggling millions of different tasks, managing all your apps, your files, memory, network connections, all at the same time. So how on earth does it keep up with all that without just completely grinding to a halt? Well, the secret really lies in solving what you could call the kernel's ultimate sorting problem. See, at its very core, the Linux kernel is just a master organizer. It's constantly sorting, tracking, and fetching just incredible amounts of data. And it has to do it all with mind-blowing efficiency. I mean, just think about it for a second. The kernel's juggling everything from the apps you have open, those are the active processes, to figuring out how memory gets divvied up. It's handling every request to your hard drive and every single little packet of data zipping in from the internet. Keeping this gigantic, constantly shifting ocean of data organized, well, it isn't just a nice-to-have feature, it's absolutely critical for performance. So, what's the magic tool for this epic organizational challenge? Well, the solution, and really the hero of our story today, is a very specific, very elegant data structure called a red-black tree. Okay, so what in the world is a red-black tree? In short, it's a type of self-balancing binary search tree. Now, the two magic words there are self-balancing and sorted. This means that no matter how much data you throw at it or how much you take away, the tree automatically, almost magically, keeps itself perfectly organized. And because it's always sorted, finding any piece of data is always incredibly fast. It's kind of like a super-powered, self-organizing filing system built right into the kernel's DNA. But you might be thinking, hey, why not use something simpler, like a hash table? And that's a great question. Well, a couple of big reasons. First, unlike a hash table, data in a red-black tree is always kept in a sorted order. But even more important is the performance guarantee. It gives you what's called O log n worst-case performance. All that really means is it's like looking for a name in a phone book by ripping it in half, then ripping that half in half, and so on. You find what you need ridiculously fast every single time. And that's the kind of rock-solid reliability a kernel just has to have. And look, this isn't just some abstract concept from a computer science textbook. Red-black trees are absolutely everywhere inside the Linux kernel. They are the go-to battle-tested data structure for a ton of its most critical parts. You don't have to take my word for it. This quote from a classic article in Linux Weekly News really hammers the point home. It shows how core components, from file systems to the all-important virtual memory manager, have been relying on these things for years. This isn't some new fad, it's a foundational building block of Linux. And the list of where they're used is it's staggering. We're talking about managing who gets to access your storage drive next. They're keeping track of all your system's memory. They organize super precise timers, manage waiting tasks, cache data for file systems, schedule network traffic. They even handle cryptographic keys. The list just keeps going. They are truly the silent workhorse doing all the heavy lifting behind the scenes. But here's where it gets even cooler. The standard, off-the-shelf way of doing things just wasn't quite good enough for the Linux kernel. The developers came up with a really clever optimization to squeeze out every last drop of speed and efficiency. So let's pop the hood and take a look. So here's the Linux magic trick. Normally, you'd have your actual data in one spot in memory, and the tree node somewhere else, with a little pointer connecting them. The problem is, making the CPU jump between those two locations costs precious nanoseconds. So the Linux way is to embed the tree node, the RB node, directly inside the data structure itself. It's a subtle change, but it's a brilliant optimization that makes memory access way, way faster. And here's what that actually looks like in a bit of C code. See that? The RB node is just another member of the struct right alongside the actual data. It's not a pointer to something off in the distance, it's baked right in. This means when the kernel is zipping through the tree, all the information it needs is right there, together. That's a massive performance win. So how does the kernel actually find something in this tree? It's a beautifully simple and logical dance. You start at the very top, the root. You compare your key to what's there. Is your key smaller? Go left. Is it larger? Go right. Is it a perfect match? Boom, you're done. With every single step, you're effectively cutting the search area in half. It's just so elegant, and it's precisely why these lookups are so incredibly fast.
But the story doesn't end there. The genius of the red-black tree isn't just about simple storage. This basic structure can actually be enhanced, or augmented, as they say, to solve even more complex problems.
The whole idea behind an augmented tree is pretty simple. You have each node store a little bit of extra information about all the other nodes in the branch beneath it. For instance, a node could keep track of the largest value in its entire subtree. Just by adding that one extra piece of data, you unlock a whole new world of powerful queries you can run. And a perfect real-world example of this is something called an interval tree. So imagine the kernel needs to find a new spot in memory for a program. It has to check and check fast if that new memory range overlaps with any of the thousands of ranges already being used. By augmenting a red-black tree, the kernel can answer that question almost instantly. It's an incredibly powerful technique, and it's absolutely essential for things like managing virtual memory.
So there you have it. The red-black tree is truly a masterpiece of computer science, working silently, tirelessly in the background to make the technology we all depend on both fast and reliable. And that really leaves us with one final thought to chew on. What other elegant, invisible structures like this are out there, quietly powering the tech that you use every single day?